Okay, so let's go back to this idea of basis of image and rank of a linear map. First a definition, but it's really nothing new. You already know these kind of things. We've got a linear map F that goes from space E to a space F, and we assume they are all both of them finite dimensional. So we're going to call the rank the dimension of the image of F. Of course, it's going to be finite dimensional because it's a subset of the space F. Okay, and it's really exactly the rank of a matrix that you used to know. It's the dimension of the column space. Okay, we just saw previously that any y that belonged to the image of F was actually given by if y is equal to f of x, it means that there exists x such that y is equal to f of x, and x belongs to E, it means that x can be written as a linear combination given a basis E1, En. Let's assume E has dimension n of E. We have that x can be written as x1 E1 plus x2 E2 plus xn En, where all the xi belong to R, okay, and ei are the basis vectors. So that's the unique linear combination that gives you x in basis E1 up to n. The xi are the coordinates of x. Okay, you can see that as a coordinates. Anything that is in a finite dimensional space, you can really imagine that you're working in Rn. Okay, so if that's your x, you know that y is going to be x1 f of E1 plus xn f of En, so that we obtain that the image of f was spanned by the image of E1 up to f of En. Okay, so if you can find the rank of this family of vectors, so which is just going to be the rank of the matrix that has f of E1, f of En as columns. Okay, it's really the column space. The dimension of the column space is equal to the rank. Okay, dimension of column space is equal to the rank. Okay, it's really the usual definition that you worked with. Okay, next thing, this theorem 18. Actually, that theorem 18 is more of like it's really you just have to write it. Okay, it's surjective. It means that for any y in the image in the codomain, you can find an x in the domain such that f of x is equal to y. And so if the image is equal to the whole codomain, then you know that you can find some x, so it's surjective. And the other way around, the direct implication, actually it's just the definition. Okay, now let's have a look at this corollary. If f is finite dimensional, big F, then f is surjective if and only if the rank is of f is equal to the dimension of f. Okay, so that's actually very simple. It's just it comes from Grassmann formula and the consequences of the Grassmann formula, which more or less tells you that if you've got a finite dimensional space, let's take we don't have to take n. We can say that let's put that the dimension of f is equal to p. It doesn't have to be equal to n. What I know, on the other hand, is that p is smaller or equal to n if f is surjective, Why do I know this? Because I know that that's one of the consequences of, well, it's really linked to this theorem. Why do we know this? Okay, we saw that the image of F, well, of course, it's going to be a subset of F. So I know that the dimension of the image of F is going to be smaller or equal to the dimension of F. In other words, the rank of F is smaller or equal to, we chose value P. Okay, but on the other hand, we saw that the rank of F was equal to the dimension of the spanning set, the set spanned by family F of E1, F of En. Okay, so this, we have a spanning family of size n, so we know that the dimension of the space is going to be smaller or equal to n. Okay, so I know that the rank of F is smaller or equal to n. All right, and if I had P bigger than n, I would be sure that is strictly bigger than n. I would be sure that F can't be surjective. Why? Just the idea is that this set won't be able to span a space of dimension bigger than n because we only have n elements. Okay, so I won't be able to make a basis of size bigger than n. So if I've got that P is bigger than n, for sure the map can't be surjective. Okay, that's one thing. The other thing was, well, what about what's happening? That's exactly the corollary. But if rank of F, so the dimension of that spanning family, is equal to P, well, that's again, that's just using Riemann formula. You've got this spanning family is spanning a set of a linear set of dimension P, and using Riemann formula, the only set of linear subset of size of that has the same dimension as the space is the space itself. Okay, so we really have that the dimension of the image of F. Sorry, we then have that it does imply that the image of F is actually equal to the whole set.